Being here tonight. This is great. Love being here with you. So Michelle made some parts, or her section made some parts that worked very, 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 very well on a mission that flew from here to Saturn and orbited Saturn for 13 years. And I get to talk to you about that. My day job with JPL is on the other end of JPL from Michelle. I'm in flight operations. I led the real-time flight operations engineering for the Cassini mission. Before I forget, please carry away a bunch of these handouts. There's two different big sheets, and then there's some big posters around by the entrance. One other thing I want to start passing around here. Whenever you see a spacecraft, whether it's being designed for Earth orbit or for interplanetary flight, it'll look gold. It'll look like it's got covered in gold. Why do you always make your spacecraft golden, people ask me. Well, you've seen Kapton. You probably use it on your 3D printers or whatever projects you're working on. Kapton is like a mylar. It's a thin, well, any thickness sheet of plastic. And then when you put aluminum on the back of it, it looks like a birthday balloon. It's not really metal. It's aluminized Kapton. This is typical multi-layer insulation that I want to pass around. It does a real good job of keeping the spacecraft thermally controlled and protecting it from dust hits and things that might hit it. Anyway, what I want to talk to you about is why would one go to Saturn? The journey, that's my favorite part. And some of the results. I'm not going to stick a whole lot of time into the results because the results are online. Go to saturn.jpl.nasa.gov and you'll see all the results from the mission are all available. So first, however, I want to start off with a 2-minute movie by way of introduction. It's got animations and a lot of actual images from Saturn. There's our spacecraft. There should be some sound, I think. Did we plug in the sound? Any questions so far? Yeah. What do you mean opposite ends of Michelle? Well, Michelle is in the hardware building and testing and designing. I'm in the cockpit flying it. Real-time operations. Can you say those names? Oh, the Cassini it's named after the 17th century astronomer Giovanni Domenico Cassini. And the probe that we carried to the Saturn system, I pronounce Huygens, but I gave a presentation to a bunch of Dutch students, and they corrected me, and it's more like Huygens. That's not quite right, but it's more a guttural. And Christian Huygens was the person who invented the pendulum clock, and he discovered Saturn's largest moon, Titan. Titan is amazingly... okay, I'll let the movie play for 2 minutes. Thank you. That's the moon Iapetus.
Slowly, people started to gather around these images, which no one had seen. close-up images flying right over the tops of the rings. And they were just goosebumps. It's a memory I will never forget.
Girl is my boss.
Cassini has changed the paradigm of where we might look for life. You could be a world around a giant planet and have conditions that are right for life.
From the Huygens probe, lakes on the surface of Titan.
It's just a monumental machine. It's the individual people that all put their pride in putting this together and building it right.
And then, in Cassini's final orbit, plunging into Saturn, measuring the composition of Saturn's atmosphere, sending back science till the very last second. We'll continue to learn from Cassini long after the end of the mission.
So why Saturn? Well, that's why. That's a typical view from a good telescope, like out on the street on Colorado Boulevard under the street lights. You can get, if you've got a good telescope sitting out there or in dark skies, no matter where, you can see a view like that of that planet. The planet is all gas, it's all hydrogen, a little bit of helium. It's 10 times the diameter of Earth, and those rings going out towards the inside, that's the A ring, that's the B ring, and you can see a little bit of the C ring up against the planet. The division between the A and B rings here is this dark area that was discovered by our scientist in the 17th century. Yeah. Oh, like a rap star? Oh, I see. Okay. Cool. Now, when Galileo saw this object in the sky in 1610, it blew his mind. He had already discovered the moon's orbiting Jupiter and broke the news to humans that we are not the center of everything in the universe because there's moons going around some other body. And then he looked at Saturn, and the rings he couldn't focus, he couldn't resolve. They just blew his mind. I could go on, but I think I won't. So it's the rings. Go there to study the rings. The rings are a system of things orbiting a center, a central object. If you're a particle in the rings, you go around in a matter of hours, even though the planet is gigantic, 10 times the Earth's diameter. 5 hours to go around in the inner ring, 15 hours to go around in the outer ring, as opposed to 250 million years in another disk system. This is a galaxy. Probably looks very much like our own galaxy. And so the same physics apply. You have an orbiting laboratory in the rings of Saturn. Other disk systems, a forming solar system. Maybe this is an early picture of our own solar system, while the planets are forming out of a ring system, a flat orbiting disk. And if you're an atmospheric scientist interested in atmospheres, you love a planet that's all atmosphere. And the moons. Here's Enceladus, that little 500 kilometer diameter moon made of mostly ice and rock down inside that has a global ocean. And it's offering free samples, spewing these samples out into space constantly. Geysers, once we discovered the geysers, the science team said, let's fly through them. And so the navigators, who are phenomenal, everything's moving. Saturn's going around the sun, Earth is going around the sun, Earth is rotating, Enceladus is going around Saturn. Everything is moving, and they put us 25 kilometers off the deck. That's a 500-kilometer diameter there. So what's 25 kilometers? We did that. We flew through the plumes, measured them, figured out what they're made of, mostly water, lots of organic chemistry. So the moons, here's another moon. This one is only 150 kilometers long. Hyperion is spongy. It's density. We can measure the density of these things. The density is less than that of water, so it's got a lot of open space inside there. Iapetus, that we saw in the movie. In the movie, we saw the mountain. If it were darker, you could see that it sticks up 13 kilometers high around the entire equator of this weird moon. This is more like 1,500 kilometers in diameter. And when Cassini, the astronomer, discovered Iapetus, he could only see it when it was on the west side of the planet. When it went around to the east side, it disappeared. And he correctly surmised that A, just like our moon, it keeps the same face tidally locked to the planet, and B, one half, the leading half, was full of dark stuff. That's the scientific term. And the whole leading hemisphere is as dark as tar, and the trailing hemisphere is as bright as freshly fallen snow. If you look at the boundary between them, zoom in, you find that it's very clearly separated blotches. And there are thermal reasons for that the scientists understand. I'm not a scientist, therefore I don't understand it. But this slide, though, was brought to you by that computer company. And the neighborhood, it's go to Saturn to learn about your neighborhood. What's it like to live in a solar system? What's it like to live in a planet? You start to build knowledge about your environs. Speaking of neighborhoods, this is the neighborhood in Teaneck, New Jersey, where I grew up. When I was 7, I guess 6 or 7, my grandfather and my father got together and built this 16-foot-tall rocket ship in the backyard, painted it all aluminum, and so my friends and I are seen in the newspaper here flying around the solar system. I was well prepared for my job. So nowadays you can find me, here's some Europa people out on the sidewalk. Here's my telescope trained on Europa, because that moon of Jupiter has got that warm, that Michelle mentioned, a warm saltwater ocean where could there be life? And if there is life, then is it DNA-based, completely separate genesis of life? Are they related at all? And so far we have a sample size of 1 for life on a planet. If life is discovered right in our backyard, what's that mean? It means life is ubiquitous. It can evolve anywhere. If there's not life there, well, look at the next place. So the journey is pretty fascinating. We spent about 7 years getting out to Saturn. We used the gravity assist technique. I'll mention a little more about that. But we built a spacecraft thanks to mechanical people like Michelle's sections, and we flew it. So let's have a closer look at the spacecraft. You can see some of that thermal blanketing with the kapton, the aluminized kapton, already in place on some of the instruments. That's the German dust detector, cosmic dust detector, that every particle of dust that encountered it, we could measure the mass, the chemical species, the electrical charge, several other parameters. The instruments are all bolted here. to the spacecraft. My friend Preston, sitting down there, is holding a nice 3D printed Cassini model. He printed that. You can use just a common FDM printer. It's got a dozen or so parts, and it clips together into a pretty nice 3D printed Cassini. Now look at the poster in back of it. That's the poster that we've got out front. So please grab all this stuff. I don't want to be carrying this home. So back to our spacecraft, that big hat, the communications dish up on top, was used for radar imaging using synthetic aperture radar technique, where you point that dish at Titan as you go by, and you can see through Titan's otherwise opaque atmosphere and see what's on the surface. And with that, we measured and discovered these lakes on the surface underneath the cloudy, hazy, opaque atmosphere. And also for communications and navigation. So we would turn that spacecraft upside down and point it at huge antennas on Earth. These are of the Deep Space Network. There are 3 locations around the world. Out in the California desert, it's called Goldstone. It's near Barstow. They give a good tour out there, by the way. Another complex is in Madrid, Spain, and another one in Canberra, Australia. So as the Earth turns, at least one of these complexes can see something orbiting Saturn or crawling around on Mars or investigating Venus or Voyager in the deep part of the outside the solar system. And there are 3 or 4 times as many users competing for the Deep Space Network than there are actual antennas to serve them. The communications are one thing. We use digital communications. The navigation tracking data is another thing. We used line of sight measurements of distance. We'd send a pulse out, spacecraft would recognize the pulse, would know how many nanoseconds it takes for the electronics to turn it around and send it back. And so we could measure the distance, line of sight to the spacecraft constantly during, say, 9 hours of a day, down to a precision of 1 meter or so. Within 1 meter, you know where the spacecraft is. And the speed, that same line of sight radio link, guess how you measure the speed? Doppler. Yeah, you measure the Doppler shift. And using the Doppler shift, you can navigate basically any spacecraft with a speed measurement of less than 1 millimeter per second. Now, I like to belabor that. I'm going to hold my hands 1 meter apart, and I'm going to clap my hands together at the rate of 1 millimeter per second. Ready? So how long is it going to take? 1,000 seconds. Yeah, at 1 millimeter per second. So I'm driving home the point that it's a very tiny increment of speed that you can measure very accurately 1 billion miles away. In fact, we commonly navigated Cassini using a precision of 1/100th of a millimeter per second. Let's see, what else about the DSN? Oh, here's my friend Todd holding up a measurement. You know, a milliwatt, about 3 milliwatts are necessary to drive your cell phone in sleep mode, 3 milliwatts. And the power of the signal coming back and having been collected by a 70-meter diameter reflector dish and then fed through its first stage of amplification is of the strength of 0.15 zeros, 251 milliwatts. And that's plenty of power to do everything you need for navigation to a digital communications. The Deep Space Network has been an amazing organization to work with. So our spacecraft, then, I mentioned that the instruments are all bolted to the side, so if you want to point the camera or spectrometer, you have to turn the whole spacecraft. And the optical instruments there covered the whole spectrum from infrared all the way up through visible and ultraviolet in imaging and spectroscopy. Really thorough coverage of the spectrum. So normally, to control the spacecraft, you can use one of two ways. You can use these little rocket thrusters. There's 4 struts coming out at the bottom, and you just make little 1 Newton rocket thrusts. But for finest pointing, for pointing your cameras, you'd use these reaction wheels. These are 10-kilogram wheels that are driven by an electric motor. So if you want to turn your spacecraft one way, you spin the wheel with the electric motor the other way. You trade angular momentum back and forth between the wheel and the whole spacecraft in 3 axes. Here, my attitude control engineer friend, Luis Andrade, is going to demonstrate how that works. That's about the same mass and size of one of Cassini's reaction wheels, and that's my electric drill. It's kind of dangerous. I wouldn't try this.
Nice. Okay, wave to the audience.
All right, thanks, Luis.
Physically, what was that wheel on the drill?
That's a garden paving stone, about 20 pounds worth. So it's a rocket ship, and it depends on those little thrusters. And then the main engine's down here, whose cover was made by Michelle's team. We'd open the cover and close the cover with that actuator. It was designed for some number of operations. I don't know, maybe it was 20, 30 or so. But we went like 10 times as many operations on that with our extended mission, extended mission, extended mission. And it always worked just great. But the rocket itself, it's got that normal-looking rocket bell shape that all spacecraft have. And that's thanks to a steam engineer. In the late 1800s, Gustave de Laval needed a nozzle to spout steam as fast as it could. He wanted a high velocity coming out of the nozzle to spin a turbine, a steam turbine. And so he did all the experiment and design and math at high temperatures and pressures. He worked out the fluid dynamics and developed the shape such that if the gas is moving this way, at the throat of the venturi there, at the most narrow point, if you reach the speed of sound, Mach 1, marvelous things happen. That exit velocity that you need for space travel skyrockets. Pun? Anybody get the pun? And it's at the expense of temperature and pressure, which is good if you want to avoid melting your engine. So we applied that principle and took off in 1997 and flew for about 7 years to get out to Saturn. Here's the flight plan. There's the sun in the middle. What has happened to my laser? Is that beer on it? Okay, yeah. Do not put beer on your laser pointer. So there's the orbit of Earth, that fine gray line going around the sun. Everything goes counterclockwise when you look down from the north. And we fired off Cassini and then slowed it down compared to Earth, and it dropped inward towards the sun. We passed by Venus. That gave us a kick using gravity assist to get out, and we followed that blue path now. Got as high from the sun, climbing away from the sun's gravity, about the same distance as Mars's orbit. And then we came back around. Each of those loops is about a year, and passed by Venus again, passed by Earth. Those two gravity assists gave us the kick to get out into the outer solar system, where we did it again to Jupiter. And I'll say it's to Jupiter because the way gravity assist works, here's Jupiter hauling its mass around the sun, huge amount of mass, great distance, 500 million kilometers or miles out from the sun. And you sneak up behind the planet with your spacecraft. And of course, Jupiter pulls in on your spacecraft because Jupiter's got gravity. The spacecraft has gravity. It's a physical object in the universe, and it has its own little bit of gravitation. And the spacecraft pulls back on Jupiter, slows it down ever so little. You can't measure it, but you can certainly calculate it. And that, slowing down Jupiter, connects you. It's called an elastic collision, so that you can soak up Jupiter's momentum and get a kick for your spacecraft. It's almost like a baseball hitting a baseball bat hitting a baseball coming in. You transfer momentum from the huge source of momentum and kick your spacecraft out. That was invented by a student working for JPL in 1961 during the summer student. As we flew by Jupiter, we took some pictures. There's Jupiter, the planet in the back. There's the little moon. Anybody recognize that orange-looking moon? Io, with volcanoes going off constantly. And there's Io's shadow. So here's the student, Michael Minovich. Last I checked, he's working at a pharmaceutical company in Los Angeles. But he worked it all out. And for the cruise from Earth to Saturn, we gained a huge amount of delta V, change in velocity. Using our own thrusters and engines on the spacecraft, you'd burn the engine and get a little delta V of maybe a meter per second, maybe a tenth of a meter per second, maybe 10 meters per second, in that area. But using gravity assist, the planets gave us 22,000 meters per second. That's a lot of fuel that we didn't have to carry. And then for orbiting in the Saturn system for 13 years, we used Titan, flew by Titan, the big, heavy, 5,000 kilometer diameter big moon of Saturn. And that gave us 90,000 meters per second. All we had to do is make little adjustments on the timing and direction to fly by Titan each time. So we flew by Jupiter, cruised for another while, and then we got to Saturn. And here's a quick little way for you to join us in arriving at Saturn.
Good evening and welcome to Cassini-Huygens Mission Control at NASA's Jet Propulsion Laboratory in Pasadena, California. The flight team is in place for SOI, that is Saturn Orbit Insertion, and that is when the spacecraft must be captured by Saturn's gravity or it will fly right on past the planet and the mission is over.
Time to turn back around to the SOI burn attitude or pointing position and light up the rockets.
We have a Doppler signature with engine turn on. Do that.
It's 9:05 p.m. Pacific Daylight Time. The SOI burn is approximately 92% complete, and we expect to track the Doppler now through the end of the burn.
That engine burned white hot for 100 minutes.
The Doppler has flattened out.
Okay, we have burn complete here.
4 years for this moment.
Well, it was 4 years for Shin there, but maybe 20 years for others. So we flew every which way around Saturn. High inclination, low inclination, close in, far out, to sample every part of the magnetosphere and every one of the satellites, the natural satellites. There's Titan, where we flew by Titan very often to get the gravity assist. So results, as I said, I'm not going to spend a whole lot of time on the results, but here's what we saw on approach in 2004 before going into orbit at Saturn. Look at this huge thing, 10 times the Earth's diameter at the equator. It's only 9 times the Earth's diameter. It's fat around the middle because it is a rotating ball of gas. And look at the rings. You can see the A ring, the B ring, C ring. Look at the shadow, the strands of the C ring, the Cassini division between the A and B rings, and look at the sunlight falling through the Cassini division and lighting up the upper blue sky above the brown haze that's lower down in Saturn's atmosphere. You can never see this from Earth. Looking at Saturn from Earth, all you can see is a fully illuminated planet and maybe a little bit of shadow around the edge of the planet falling back on the rings. But look at the shadow on the rings off to the up 90 degrees or so, the night side of the planet. Yeah. And we got our spacecraft around into the shadow of the planet. From there, we could safely turn the instruments back and look towards the sun and Earth. You'd never do that without being in the shadow, because the sunlight would burn out your optics or your image sensors, which on Cassini were all CCDs. Well, I can literally go on for an hour about this one image, but I won't. But I'll tell you that, see that faint ring out there? You can see it because it's very faint particles lit up from behind, and you're seeing forward scattered light now. Just like driving in the sun, your windshield, you see all the fine dust as you're going towards the sunlight. You go, okay, it's time to clean the windshield now. But also, the B ring shows that it's opaque. It's not permitting a lot of sunlight to come through. The A ring is lighting up a little brighter. The C ring is lighting up from all the fine particles in it. And now you can see the D ring inside. This bright strand is a very thin strand. It's a little bit overblown because of how bright it is. We'll see that it's the F ring. We'll see it closer up a little while. It's freshly ground ring particles. I'll show you what that means. And so the fresh grinding of all those ice particles in the rings means that they're very fine and they light up very brightly. Now, and this is one of the lithography pages I want to give out. I don't want to take any of these home, so please grab some for your friends. This is natural color. It's what you would see if you were there. And these are not image flaws. They are little shadows of the rings refracted around through the atmosphere, sunlight refracted through the atmosphere. The sun is right about here, back there. And so now you can see all the rings. You can see the A ring, the B ring, the C ring, the D ring, the E ring. I was thinking about getting an E ring. The E ring is created by Enceladus's geysers, that little moon that's got the geysers going off constantly. If those geysers on Enceladus shut off, that E ring would sublimate away in probably tens to hundreds of years. And then there's that little dot. See that little dot on the left? Zoom in on it. There's the F ring. There's that little dot. Anybody know what that little dot is? Cassini? Earth? Somebody says Earth. Well, let's take a closer look. Yeah. Yeah, we saw Earth. There's Titan. There's a natural view of Titan, except that you have to be at the Saturn system to be able to see the night side of Titan. High atmospheric haze turns blue. That's where the methane it's a nitrogen atmosphere, just about the same density as Earth's nitrogen atmosphere, a little bit more. 5,000 kilometers in diameter, so it's a great big moon full of momentum that we stole a lot of. Don't tell anybody. So chemistry happens. The sunlight hits that methane high up there. Methane is what, CH4? Carbon and 4 hydrogens. They all break apart in the ultraviolet light. And then they recombine and snow down onto the surface. They create hydrocarbon snow that moves around in dunes. There's an infrared view looking through the atmosphere with our instruments. You can see clouds. These are the dark lowlands where those dunes of hydrocarbony stuff landed and got blown around. I think I'll skip this movie in the interest. Oh, no, that wasn't the movie. Okay, this is a nice synthetic radar image of one of the lakes of methane. It's very cold. It's 90 kelvins on the surface of Titan. So the rocks are made of water, and the liquid is made of liquid methane. This is the movie that I'm going to skip. And there's the F-ring that I've been quacking about so much. And I call it freshly ground because this little moon, Prometheus, orbits Saturn in a slightly more elliptical path than the F-ring particles. And it comes out once every 15 hours around Saturn, no going this way, and it clobbers the F-ring. Actually enters the ring and helps grind up the particles and makes them fine. This was taken at solstice, where the sunlight was edge-on to the rings. So look at the shadow of Prometheus cast across the A-ring. Here's the F-ring again. Little Prometheus having done its deed there 15 hours before, the time before. And this series of images is an actual series of pictures looking outward towards the F-ring, catching Prometheus in the act. Then we went into the shadow of Saturn, but after we came out, there's the damage having been done. Would you like fresh ground ring particles with that? This is Enceladus. This is the 500-kilometer diameter little moon, little ball of ice, with the South Pole showing crevices, and there's, with the sunlight from behind, lighting up the fine particles that are streaming out. It's a rate more than, say, the Yellowstone Old Faithful geyser, and they just go off constantly. And they kind of seep out of the crevices around the South Pole. So flying through them, we discovered it's mostly water. There's a lot of NH3, ammonia, organic chemicals, hydrogen, all pointing to a warm saltwater ocean with a high likelihood of thermal vent activity. Like in our oceans, we have these thermal vents that are volcanic vents on the seafloors, and in some places there are little communities of life that have never seen the sun. So that's a possibility for life elsewhere in our solar system. Enceladus is one of the places that we want to go back and have a good look. So we finished up the mission by taking a gravity assist Titan that put us into 20 of these orbits that came in as close as the F-ring. So we got really good up-close images of the rings and of Saturn. And then these blue orbits, another gravity assist, put us through 22 of those, and the final one we burned in, became a meteor with our spacecraft into the upper atmosphere of Saturn, going 125,000 kilometers per hour. Here's a look at the final path in. There's the September 11 flyby of Titan that soaked up enough of our own momentum, the spacecraft's own momentum, that it couldn't climb as high on the way in, and so it burned into the atmosphere instead of making another loop. Took the last image right there, September 14, half a day before, played back the data, and then switched to a mode where all the data had been played back off of the recorders, and we had switched to a mode where the instruments were sending their data directly back to Earth, measuring the in situ components, the atmospheric composition and whatnot, right to the last second. And here is the final picture that was returned. This is the night side of Saturn now. There's a little bit of the sea ring in there. And here's this big dark equatorial band. If you were floating in a balloon or blimp in that equatorial region on the night side of Saturn, you'd look out to the rings and wouldn't see them because you're edge on to the rings from the equator. And the rings are hundreds of thousands of kilometers wide, but only a few meters, maybe tens of meters in thickness. And so from there you can't see them. And correspondingly, no ring light comes back to light up the atmosphere. So this is all ring light up here and down here, and that's the dark night of Saturn. Here's the view that we had. My team works in this room. Have you been to JPL for a tour or open house or anything? This is a familiar spot. There's an open house coming up. I think it's in June of this year. They'll announce tickets, and then you got to watch out for tickets because they go away real quick. Mission control, there's my ace Mike, and this is the data. My team's job was to watch the engineering telemetry coming back from the spacecraft to make sure that all the temperatures and pressures and computer states and everything were proper. And if anything was out of limits, we'd take action. What? Like what? What kind of action? Well, if say it was a temperature going too high on a thruster or something, we would call the propulsion team. They would come in, they'd analyze their data. Often it would be an instrument acting up. Like we have a magnetometer, a magnetic field sensor sticking out on the boom. Take a look at that little effigy I brought back there. The magnetometers are hanging out in the breeze, and every once in a while they would decide not to talk to the bus anymore. And so you'd have to send up a command to reset the magnetometer bus interface unit, and lots of little things, but thank goodness very few serious things ever happened. Here's the signal that we watched for 20 years. It's a big booming, that's the noise, and that's the signal from the spacecraft in around 8,000 megahertz. And we also had a signal turned on at this point at around 2,000 megahertz, so we had two signals coming in. And there was a third, actually. But that's the X-band signal that always carried all of our navigation and telemetry and whatnot. So I'm going to finish up showing you another 2-minute movie as kind of a summary. That's actual sound from the plasma interacting. There's an opposition effect rainbow. Jet streams. Actual plasma sound and the aurora, the refraction through the atmosphere of the rings and shadows. Edge-on views showed some vertical development in some of the rings. There's our friend Prometheus and its companion Pandora. How dark the B ring is when it's lit from behind. Storm was observed first by an amateur and studied by Cassini. Ring shadows. Okay, so thank you very much for being here tonight. It's been a real pleasure for me. And I have no idea. Thank you so much for coming.